we are working with some special cases today. So what that means is that predicting the products just gets trickier and more fun. So when you look at your reference sheet, so this is going to be something you're going to be used to always having in front of you is your reference sheet. It's on the back of that periodic table. They'll always be available for quizzes and tests. So you're going to see that you've got some special cases that are mentioned for you. Notice what's missing, though, on the reference sheet. Actually, I don't know. Let's see. Your reference sheet, it's missing because that's the one that will be used in class. You don't have all these handy little examples next to it. So that kind of takes something away from it. So maybe even get used to using those so that you don't rely on the examples. But right now, while we're learning this, we can look at the examples, and we see that there are some special cases, mainly for the types of reactions such as decomposition, synthesis, and double replacement has a little. Notice that single replacement is missing from this list, and also combustion, because there's really nothing special about those. So starting with decomposition, actually let me mention, these are just the opposites of one another. So to be honest, all of these special cases that you see for decomposition, they will also be there for synthesis, but just in reverse. But they're not as common, so we just have the more common ones listed. But you could easily go back to decomposition and just look at it in reverse and see those situations. I am not going to read all of these because the key here is that we want to go through some examples, and we will hit these when we go through the examples, but make sure you just understand what this is saying. If you have a metal chlorate, well, the metal might be something like potassium and chlorate. So potassium chlorate, what happens is it decomposes, it breaks down to form metal chlorides. So in this case, it would be potassium chloride plus oxygen. And so you just have to relate these to all of your special cases. Notice these are still easy to identify. If you are given the reactants and all you're given is this, you easily know that that's going to be a decomposition reaction because you only have one reactant. So that makes it really easy to identify. But the difference here between what we're seeing and what we saw yesterday is the presence of which element. What do you notice in your reactants for all of these elements? Oxygen. So really what you're doing is you're getting some polyatomic ions in there that have oxygen in them. So instead of just saying, hey, it breaks down to the metal plus that polyatomic ion, it's a little trickier than that. You have to break it down to, instead of sodium plus nitrate, it becomes sodium nitrite plus oxygen. And I'm going to go back to this now. You will always have this material given to you in your reference sheet, so you do not have to memorize it, which is a fabulous thing. But just make sure that you, just make sure that you know how to use them. That is not a plus. That is a hydrated salt, so that's a dot. That should have been higher. But anyway, here are our special cases, and we said that single replacement was missing from this list. I just went ahead and put this in here because we're going to want to refer to it. But remember that your activity series, whether it be for your metals, which you use this for, or your non-metals, which you look at your periodic table for, you only use your activity series for single replacement reactions. And then yesterday, we also practiced how to use this information. This is always just talking about hydrogen. So these four, for example, are really, really strong and active, meaning the water can be cold and it can still grab that hydrogen out of there and displace it. So as you move on down, the metals are not as active, so it would not be able to displace the hydrogen from cold water. It might just be from steam or from an acid of some sort. Okay. Our rules, really we corrected our rules. I like to say my number one is to go ahead and write the formulas for reactants. I like to do that right up front because lots of time, especially when we start looking at the tricky things, today's special cases, lots of times that's going to help us decide what type of reaction it is, and that's really important for how we go ahead and predict those products. So you do that, then you predict your products, and you balance afterwards. You never try and balance while predicting the products. Okay, here are our examples. First one, we have hydrochloric acid plus sodium sulfate, or sulfite, I'm sorry. So sodium we know is +1, sulfite is SO3 with a -2. What type of reaction is this? Double replacement. Okay, so now we just identified this as a double replacement reaction. So what you need to get into the habit of doing is having that reference sheet right in front of you, and you think double replacement reaction. Is this just pretty straightforward, or is there some special case that I should be noticing? And the answer is there is a special case. Looking at your reference sheet, and they're numbered, so that might make it easy for us to refer to. Do you see which number double replacement this might be referring to? Number 2. So we have, number 2 says an acid plus a sulfite. So that's this situation. We have an acid and we have a sulfite. So whenever that's the case, it's going to yield a salt plus water plus sulfur dioxide. So you know that your salt that's going to be formed is always going to be the odd guys out. So in other words, your sodium and your chlorine. Purely coincidental that it's sodium chloride, just the regular salt that we think of. But that's the salt that it forms, sodium chloride, plus water, that's from the hydrogen right here, and some of this oxygen, plus the sulfur dioxide gas, which is produced. Now, we've been saying if you can keep your polyatomics intact, do so. You can't in this case. What happened is it really did form sodium chloride, and then it formed hydrogen plus that sulfate, which is your, sulfite, which is your sulfurous acid. So what happens in that case is that sulfurous acid is not stable. It breaks down to form water plus sulfur dioxide. So that's what happened there. We come back and we balance, and 2 and 2, and that should do it. So that's our first special case we look at. Okay, number 2, here we have arsenic acid. So arsenate. Anybody remember arsenate? ASO4. What's the charge of arsenate? -3. So there's arsenic acid. It's heated. What type of reaction? Decomposition. So we would look at our decomposition cases. Do we see any special? So number 5, it says some acids decompose to form water plus a non-metal oxide. So in this case, our non-metal oxide is going, and lots of times I like to write that first. Well, it doesn't really matter. You can say your water plus your non-metal oxide, which is going to be your arsenic is considered your non-metal. So in this case, we're going to call it some sort of ASO, but we don't know what the charge is, what these subscripts need to be. Or not even charges. We have to think about the numbers of those, because remember, we're talking about a non-metal and a non-metal. So what we need to do is a little bit of additional work. If we come back over here to this guy, you know the charge of hydrogen. What is it? +1. You know the charge of oxygen, which is -2, meaning I have a total for my hydrogens. I have a total of +3, because I've got 3 of those +1s. And for my oxygens, I've got a total of -8. Remember, this is a neutral compound. It's got to equal 0. So what does the charge of my arsenic have to be? +5. So if it's +5 on this side, it's going to be +5 on this side. So I'm thinking to myself, this is +5, this is still -2. So the way we would write that is AS2O5. When you come back and balance, then we look at this, and I've got 2s and 3s for my hydrogen, so let me try this. So I've got 2 arsenic, I've got 8 oxygens, everything's good, I think. Okay. So notice we had to do a little bit of extra work. That's the case when you have nonmetals in there that you're forming. That's some sort of, notice this was a covalent compound. We did end up thinking about our oxidation numbers, but it wasn't real straightforward to us as to what the charges were, so we had to go through that process. Okay, next one we have nitric acid, +1, -1, plus barium carbonate, +2, -2. What type of reaction? Awesome. So we know it's double replacement. We might think, oh, I'm just going to make barium nitrate plus carbonic acid. But what happens is that carbonic acid is not stable, and we see from number 1 that it breaks down to form that salt plus water plus carbon dioxide. So when we do this, we get our salt of barium nitrate. Barium's +2. Nitrate is -1. Plus water and carbon dioxide. So now when we come back to balance this, I will try a 2 there for my hydrogens. My nitrates look good. I've got 1 barium. My oxygens look good. Everything in carbon. So all is good. Okay, hydrogen peroxide. You guys know how to write hydrogen peroxide? Good. H2O2. So remember, peroxide is O2 with a -2 charge. So it's a little bit different than your regular oxygen. So we have this, you know, hydrogen peroxide, you don't even need to heat it. You just kind of have it in a bottle or sitting out, and it's going to decompose on its own. That's why it's in those brown bottles, so that the sunlight doesn't decompose it. But if you heat that up, it's going to decompose down into something pretty quickly, which we just answered. This has got to be decomposition. So what number is that you see? Number 8, peroxides decompose to form the metal oxide, in this case, the hydrogen oxide. Well, what is hydrogen oxide? Again, water. That's all it's going to be in this case. It's going to, the metal oxide is water, hydrogen oxide, plus oxygen. Oops. Okay, so we come back and balance. And I'm going to fix the fact that that was an odd number, so I fix it like that, and like that, and that fixes it. Okay. Next one, strontium chlorate. So Sr with a +2, ClO3 with a -1, and it's heated. So again, that's got to be a decomposition reaction. You're getting in the habit of not just decompose. Here's the common mistake, that people just look at that and go, oh, it's going to decompose. I'm going to make it turn into strontium plus chlorate. That doesn't make sense. So when you look at it, where do you find that the number 1? So it's going to form strontium chloride plus oxygen. Strontium chloride, Sr with a +2, Cl with a -1, plus oxygen. So now you balance. And I can do this. Does that fix it? Yep. There we go. Okay, lithium oxide plus water. Lithium oxide +1, -2, plus water. I'm going to write it H2O. But if you prefer in your head to be thinking about it as HOH, because you're thinking about those individual ions, this is now a little bit, and I don't know that I needed to do that, but we talked about that yesterday with one of the situations. So maybe if you had it written like that, still, what would you think of, any thoughts on what type of reaction this is?
Synthesis number 1.
It is synthesis. This is the one that's commonly missed. Lots of times people will try and make something like this be double replacement. And if you were to try and switch positions with these guys, you find out that you get exactly the same products. So you've got oxygen as your nonmetal in both cases. So don't do that. Instead, it's a synthesis reaction. This is that case where we have a compound plus a compound yields a bigger compound. So this is a synthesis reaction. When it combines together, what does it form? Okay, which salt? What is it called? Lithium hydroxide. Lithium hydroxide. Plus 1, minus 1. Okay. And we balance it like that. All right. Number 7. Magnesium oxide plus sulfur trioxide. Plus 2, minus 2, plus sulfur trioxide. This looks like this might get a little tricky because it's a covalent compound. We know how to write it very easily. But then we have to think about, is this going to be some sort of special case that's going on? Look around, think about what type of reaction do you think this is going to be? It is a synthesis reaction. Do you see the special case? Yeah, it's number 1. So a metal no, it's not. It's number, metal, yeah, number 3, sorry. So it's a metal oxide plus a non-metal oxide. You've got your metal oxide, you've got your non-metal oxide. So in this case, it just tells you that it's going to form a salt. Maybe you're wondering what salt it would form. So you've got a couple different possibilities, and this is where you know you're going to have to do some extra work again. So it's up to you guys. I think you've got a blank back on your notes. Maybe you want to flip it over and show what's going on. We know that our possibilities are that it can form actually, let me do it this way. We know that oxygen has the minus 2. So therefore, we're getting a total of minus 6, meaning that sulfur has to have a total of plus 6. And there's only one of them, so that one has to be a plus 6 charge, right? So our possibilities over here, we need our sulfur to have a plus 6 charge. So we know it's either going to be magnesium sulfite, plus 2 minus 2, or magnesium sulfate. Those are our possibilities for combining all of those together, magnesium, oxygen, and sulfur. So when you go through and look at your charges, here you have a plus 2. You've got a total of minus 6. Okay, these are totals. For your oxygen, so what does that mean your sulfur has to be for magnesium sulfite? Plus 4. So that doesn't work with what we just said. Here, plus 2 and a total of minus 8 for our oxygen gives us a total of plus 6 for our sulfur. So this is the answer. It's got to be that one in order for it to work out right. So magnesium sulfate. Quite often, it will just work to where you guys can look at this and say, okay, 1 sulfur and 4 oxygens. So notice how that worked, but it won't always do that. So it won't always be nice and easy like that. So as far as balancing, it is already balanced. Okay. Next one, we have zinc hydroxide, Zn with a plus 2, hydroxide with a minus 1, and it's heated. Obviously, this is going to be a decomposition reaction. Don't tell me that it breaks down to form zinc plus hydroxide. Look at your special cases. What does it form? Which is your, good. Which number? 4? So metal hydroxides form metal oxides plus water. So it's going to form zinc oxide plus water. Zinc oxide plus 2 minus 2 plus water. That's it. And then it is balanced. Okay, sulfur trioxide. This is going to be another little tricky one that we might have to do some work on to try and figure out some charges. And the way I know that is because that's a covalent compound. So sulfur dioxide plus water. Again, if you tried to make that a double replacement reaction, things are going to go terribly wrong because nothing's going to change. It's going to have the exact same products. So what type of reaction is this? Synthesis. So which synthesis example do we have? Number 2, a non-metal oxide plus water forms an acid. Well, let's come over here. An acid. What are our acid possibilities? Okay, an SO3, do we need to do anything else with that? H2, because it's plus 1 minus 2. So that's sulfurous acid, or it could be sulfuric acid, H2SO4. So we need to figure out which one it's going to be. So we come back over here. This is a total. I'm doing my totals because oxygen's minus 2, so I've got a total of minus 4, meaning my sulfur has to be a total of plus 4. So when we come over here and do our scratch work, and this is what I was saying, you could flip it over and do the stuff on the back if you wanted. We know our hydrogen is a total of plus 2. Our oxygen is a total of minus 6. Ding, ding, we have a winner. So there's our plus 4. But just to show you, here in sulfuric acid, it would end up being a plus 2 and then a minus 8, meaning that this sulfur is going to be a plus 6. So that is not the case. It's going to be sulfurous acid instead. And so we see it's H2SO3, and it is balanced. How many of these are we? I don't have the sheet in front of me. Are we halfway through? Okay, got lots of these. Okay, so the next one we have is magnesium nitrate is heated. MgNO3 2. It is heated, so decomposition reaction. What happens to those metal nitrates? They break down to form metal nitrites plus oxygen, number 2. So we're going to form magnesium nitrite plus 2 minus 1 plus oxygen. Okay, so then when we balance it, it is balanced. That's an O. Okay, phosphorus acid is heated. Tricky part on this is just remembering how to write these formulas. So phosphorus acid, what would you say? H3PO3, because this comes from your phosphite. So it is heated. What we end up seeing is that some acids, number 5, some acids decompose to form water plus a non-metal oxide. You hear that word non-metal, you know you're going to have to do a little bit of extra work on this. So it's going to form water plus a non-metal oxide. So we know it's going to be phosphorus and oxygen, but what we don't know is what these subscripts are going to be. So we come back over here, and in fact, I'm going to pause this and let you guys figure it out. Okay, everybody has come up with plus 3 as the correct charge. So if this is plus 3, this is minus 2, that is what we end up getting. Diphosphorus trioxide in this case. And it does not balance. We're going to have to go through some extra steps. So I'm going to start by putting a 2 here and a 3 here, because what caught my eyes were the hydrogens being 2 and 3. And now I have a total of 6 oxygens and 2 phosphorus, so everything's good on that. Okay. Next one is ammonium nitrate, plus 1, minus 1, plus calcium hydroxide, plus 2, minus 1. You guys can all look at that, and you know that that's a double replacement reaction. Is that a special case? Number 3. So you've got ammonium compounds plus a base. Yep, there's ammonium, and there is our base. If you're not feeling good and comfortable about that yet, make yourself a note that base equals hydroxide ion somewhere in there. And what we end up seeing here is that it's going to yield a salt plus ammonia gas plus water. You should also remember that ammonia equals NH3. So maybe jot that down if you don't remember that. Okay, so we're going to make it equal a salt. Maybe, I don't know if that's going to be the tough part for you or not, but I know I'm going to use this for my ammonia. And I know I'm going to use this for my water. So these guys right here are the leftovers for my salt. So in this case, it's going to be calcium nitrate plus, we said ammonia, which is NH3, plus water. And for balancing, we have that and that. Okay, let's see. We have 8 plus 2 is 10 hydrogens, and we have 6, 7, 8, 9, 10. Okay, let me check my oxygens. I've got 6 plus 2 is 8 oxygens. 6 plus 2 is 8 oxygens. So that should be it. Okay, we are moving on, and we have dinitrogen trioxide. Makes me a little scared because I know that's a covalent compound, so I'm going to have to think about some extra work on that. But dinitrogen is N2 trioxide O3. Covalent compound means we're going to have to do some figuring out of charges here. We're adding water. What type of reaction? Synthesis. You guys are doing awesome with that. Okay, so when we combine all of these, even if you didn't have your reference sheet in front of you, you see hydrogen and then these N's and O's. So you should see that that's going to form an acid. So the question is, which acid is it going to form? Because we know the possibilities would be nitric or nitrous. Those are our 2 possibilities for acids that could be formed. So when we come back over here, we know that nitrogen is a -3, so that gives us a total, I'm sorry, let me go back to oxygen. Oxygen's a -2, so that gives us a total of -6. So our nitrogen must be a total of +6, but there are 2 of them, so each one is a +3. So that's what we want, is we want a nitrogen with a +3 charge to it. So when I start with nitric acid, I have +1 and I have -6. That's not going to do it because that gives me a +5. So I come down here to nitrous acid, +1, -4, that's got to be it, +3. So there is our answer. So it forms nitrous acid. I'm going to balance by doing that. Okay. Yeah. Okay, next one we have aluminum oxide plus water. AlO3 plus H2O. In this case, it looks to me like we have a metal oxide plus water, which we see classified as a synthesis. So a compound plus a compound just yields a bigger compound. So what would be the name of the product that's formed in this case? Aluminum hydroxide. So Al with a +3, OH with a -1, and that's all there is to it. So that should take care of the balancing, but it doesn't, does it? There's 6, no, hold on. Does that take care of it? 3, 6, yes, there we go. Okay, sodium carbonate is heated. Na2CO3, it's heated. It does not just break down into sodium plus carbonate. You have to look at your special cases, and you see it's number 3, metallic carbonates form metallic oxides plus carbon dioxide. So metallic oxide, sodium oxide, Na2O plus carbon dioxide, and it is balanced. Okay, nickel 2-sulfate hexahydrate is heated. So now we're getting to our hydrates. In fact, we do a lab on something like this pretty soon. In this case, nickel 2-sulfate. Do you guys know how to write that? Ni with a +1, sulfate, SO4 with a minus, I'm sorry, +2, -2. And it's hexahydrate. So you put your dot right in the center, and it's going to be 6 water molecules, 6 H2Os. What do you think happens?
What's the dot?
The dot, remember when we did this with hydrates, when we were talking about molecular formulas, that's just saying that these 6 water molecules are chemically bonded to the nickel sulfate. So it is bonded. It's not just wet or nickel sulfate in solution. It's actually bonded to it. So what do you think would happen when you heat it up? It's going to drive off that water. So you guys should see this decomposition. And number 7, hydrated salts decompose to form salt plus water. So it's just that easy. All you do is you just say it's going to be the nickel 2-sulfate plus your 6 waters. So that's all you're doing is changing your dot to a plus. And that's it. So we are done. You guys are now wizards at predicting products.